Starting. All attendees are in listen-only mode.
Welcome everyone. So we're going to wait a few minutes before we get started, but I just wanted to let you know that everyone who's on logged on already, that you're connected correctly, and I can see that you're all logged on, so there's no issue there, and we will get started shortly. Hi everyone, welcome to the Nuclear Institute webinar for May. This month we have Dr. Ian Scott of Moltex Energy who will be providing an update on their molten salt reactor technology. Ian did a webinar for us this time last year, which was really the most popular webinar that we had all of 2017, so it clearly is a topic that a lot of you are very interested in, so I hope you enjoy it, and I'll pass you over to Ian.
Good afternoon everybody. Thanks for taking time out of what's a gorgeous day here. Hope it is for all of you as well. I'll start with apologies for anybody who heard me speaking down at Gloucester at EDF in the last few days, because you'll be rehearing all the material you heard then. But probably for most of you there'll be some new material here. So I'm going to start on a bit of a downbeat note. This is the latest projection from the International Energy Agency. It's their World Outlook 2017 for where power is going to be coming from on a global basis between now and 2040. I've shown nuclear with a big red arrow there because it's pretty easy to miss it otherwise. Essentially what this says is nuclear is going nowhere. All of the increase looking at there pretty much is reflected by China, and it doesn't even offset the decline in existing nuclear markets. So nuclear, best case, is going to sustain its current position. And if you look at the relative size of the source of energy there, that means that by 2040 it's going to be an almost irrelevant source of energy. That's not really good news for the nuclear industry. The reason underpinning this is fairly obvious. This is a chart from another study. This is from the EPRI, Electricity Power Research Institute in the USA. It's a 2018 report. And they did a very nice piece of work in which they used really quite sophisticated modeling tools to look at what impact the capital cost of nuclear had on its projected market share. In this case, it's market share by 2050. And this is actually really very interesting. Now, this is US market specific, but it's a pretty good indicator for the global position as well. What it's saying is that at $5,000 per kilowatt, the bar on the left, nuclear basically has no role to play. At 4,000, it still has no role to play. At 3,000, it starts to become an economically viable option. And at 2,000, it becomes the dominant power source, even in a country with very cheap fracked natural gas. It's literally all about capital cost with nuclear. And of course, where we are today is on the wrong side of that 5,000 figure, which is why nuclear is essentially going nowhere. Just to give you perspective on that, this is a graph I've used many times. It's actual data on costs, both overnight costs and total cost of nuclear power in the USA through the first nuclear era. And you can see that after 1980, it basically got completely out of control and shot above the point where even overnight cost, let alone total capital cost, it's so far above the viable level from the EPRI analysis that it's only going to be built for political purposes, not for economic ones, and therefore mostly will not be built. What happened in 1980? You probably all know the dates. We're talking 3 Mile Island and Chernobyl. And after that point, a technology which prior to that point was actually cheap enough to become a really important economic force in power generation ceased being so. Prior to 1980, countries could go, like France, almost entirely nuclear and do so at great profit. Since 1980, that has no longer been the case. So the solution is pretty obvious: fix that problem of increased safety costs, but nobody is going to simply take away the safety systems. That would not be a good move. I find it quite helpful to look at a really very standard graph from, this is from the Health and Safety Executive. You have equivalents from most of the safety organizations around the world. It's called a hierarchy of controls which are used to reduce risk. And it goes from the top, which is blue, which are the most effective controls you can apply to risk, and ends at the bottom with the least effective. Start eliminating, then substituting, then bringing engineering controls, then administrative controls and personal protective equipment. So what happened after Chernobyl, 3 Mile Island and Fukushima? Essentially, we put a great many engineering, administrative and to a degree personal protective equipment controls in place. In the context of the nuclear major risks, PPE are iodine tablets, and right now they're suggesting distributing those to the entire population of Belgium. That's going to do nuclear a great deal of good, obviously. We have administrative controls of extraordinary depth and power, and we spend a huge amount of money on engineering controls with containment domes, ultra-reliable systems and so on. What we haven't really done is the things at the top of that pyramid, which are elimination and substitution of hazards. And that is the Moltex approach to this. It is to focus on reducing risk by eliminating hazards. And there's a very good story that can be done. So let's talk about hazards. This is my diagram of a pressurized water reactor. I have a big black heavy metal pressure dome, pressure containment. Inside that you have water. Inside that you have a fuel tube, or rather a few fuel tubes containing uranium oxide pellets. So where are the hazards? Well, they start actually with the fuel. Fission, as you all know, produces gaseous fission products, and a lot of them, a typical fuel pellet by the end of its life will have produced about 50 times its own volume of gas. Mostly noble gases, but also cesium and iodine with the chemistry of fuel pellets are also gaseous. Those gases are trapped in the pellets. The amount of space for them is quite limited because uranium oxide fuel pellets are very dense, around about 5% available space. So you're squeezing 50 volumes of gas into 5% available space. You are talking about hundreds, approaching 1,000 bar pressure of those contained gases. That's huge. It's a tribute to how well we make uranium oxide fuel pellets that they actually will hold those pressures in. Second risk, of course, is then we've surrounded these fuel tubes with water at over 300 degrees centigrade. Well, you don't have to be a genius to know what happens if that pressure boundary fails. Boiler explosions have been some of the worst industrial explosions in history, and fundamentally, Chernobyl was a steam explosion. So you've got at the heart of your technology two really very major hazards: volatile, highly pressurized, radioactive fission products, and surrounded by a very, very powerful driving force to aid their dispersal. Both of those hazards can be virtually eliminated by the use of molten salts. And this is molten salts in two contexts. First, with the fuel. One of the beauties of molten salt fuel is that, first of all, no pressure accumulates. You still produce gaseous fission products, the noble gases, xenon and krypton, but they bubble out. They do not accumulate. But most important, the really bad radioisotopes in the volatile source term for the reactor, which are cesium and iodine, whereas in uranium oxide or metal, these are essentially elemental in form and therefore volatile. In molten salt, they are salts, cesium iodide, excuse me, cesium chloride, sodium iodide, for example, have extremely low vapor pressure, not the same as table salts. So you essentially eliminate the high volatile source term from the reactor, just like that. Second thing is in the coolant. Using molten salts as coolants, which is used, they're used quite extensively now in industry, have huge advantages. They are very high boiling points, so they're not pressurized. They are chemically stable. So if there's one thing that's worse than surrounding a nuclear reactor core with water at 300 degrees, quite honestly, it's surrounding it by molten sodium for fairly obvious reasons. Molten salts essentially eliminate both of these hazards. I'm cutting really right to the end of the talk here, but this sets up what this can do to the economics of nuclear. Showing here the overnight capital cost rather than the whole cost, because the whole costs just get absurdly high. With the right approach to safety, that red bar at the bottom right shows where nuclear energy can end up. And I'm going to hopefully convince people that that is actually viable by the end of this talk. That is firmly in the region where nuclear energy becomes the dominant source of power for the world. And that's what we are setting out to achieve in Moltex, and really what the world absolutely needs if we are going to stop burning fossil fuels. Okay, enough economics for the moment. Let me talk about reactor design. I'm going to do this quite quickly because this is only a 30-minute webinar. First of all, I need to explain that there are two completely different forms of molten salt reactor out there in the world. The Stable Salt Reactor, which is the Moltex technology, has separate molten salts for the fuel and the coolant. All of the MSRs are based on what was developed in the 1960s in the USA, which is a system where the fuel and the coolant are the same thing. When you have fuel and coolant the same, you pump the fuel into a reaction chamber where it goes critical, gets hot. You then pump it through a heat exchanger where the heat is taken away to do something useful. And then you return it through chemical purification systems, pass valves, drain tanks, all sorts of complications. But essentially, it works by pumping the fuel salt in such a way that it flows in turbulent form, which gives you efficient heat transfer. Moltex approach, the Stable Salt Reactor, does not do that. It puts molten salt into fuel tubes, grouped into fuel assemblies, really very, very like normal solid-fueled reactors. That brings some really major advantages. I've just listed here some of the challenges associated with pumped molten salts. You're pumping something which is radioactive in the sense that we have never really experienced before. This isn't the glowing blue spent fuel coming out of a PWR. This is actually the fuel in the core. This is emitting gamma radiation at several kilowatts per litre. It is radioactive in a way that is almost hard to comprehend. and we're pumping it around a circuit, which someday is going to spring a leak. The engineering challenges are obvious. Quickly, the other ones, because of the necessary chemistry to pump molten salts, you require new alloys, requiring new in-reactor validation to make them usable in a modern nuclear system. People talk about Hastel-ON as being something which has experience. Well, Hastel-ON hasn't been used in nuclear since the 60s, and the data produced then for its behavior would not be accepted by modern regulators. So you are looking at a new alloy. The third is incompatibility with the IAEA safeguards protocols. The agency's safeguards protocols essentially work by tracking fissile material in defined fuel assemblies. Pump systems don't have defined fuel assemblies. They have bulk fissile material where you have to know the composition and the volume precisely at all times. It can be done, but right now the protocols don't exist, and it will probably take over a decade to put them in place. Last one there, just skip over the off gas. Because of the pumped system, there is a quite sophisticated interplay between the neutronic behavior and the thermohydraulic behavior. Just one example, delayed neutrons, which normally are released in the reactor core, some of those delayed neutrons will be released in the heat exchanger. You therefore need coupled codes. It's a fascinating scientific challenge to produce those. A wonderful academic project. I wouldn't want that associated with any industrial development that I was involved in. Essentially, using static molten salt solves all of those challenges. I'll go through some more detail on those as I go through. So if it's such a good idea to use static salts, why haven't people not done it? Why is this a new concept? Because it's actually pretty obvious. And the answer comes back to a mistake. Only way to put it, really. The first molten salt reactor was developed for the US Air Force. They wanted a reactor to power an aeroplane, and they quite rightly rejected the concept of putting molten salt into fuel pins. They did consider it, and they modeled it. They rejected it because in an aircraft you can't rely on gravity. And if you can't rely on gravity, you can't rely on convection. And in liquids, the dominant heat transfer mechanism is by convection. And so they rejected the idea of unpumped molten salts for really very good reasons. In an aircraft, they were a disastrous idea. But then nobody went back and revisited that decision when we decided not to fly nuclear reactors around the world in aeroplanes. And we should have done. And that is essentially where Moltex started. We revisited that decision and showed that actually static molten salts work just fine, provided you can rely on convection. So what's the reactor which results from that? This is the very oversimplified cartoon version, but it's useful just to give you an orientation of where we are. So we have a tank with an argon gas containment above it. In the tank we have a pool of primary coolant, which is a zirconium fluoride-based molten salt. Immersed in that pool we have the fuel assemblies forming the reactor core. The fuel is a mixture of sodium chloride, plutonium and uranium trichloride that I will talk more about later. Also in the pool are the primary heat exchangers and pumps, which circulate the coolant through the core. This is an integral design. It allows all of the radioactive coolant to be held within the pool rather than pumping it outside of that containment and then having to worry about leaks. For those familiar with nuclear reactor design, this will look quite similar to a sodium fast reactor, and it is, apart from the absence of sodium and the use of molten salt fuel, except for one quite important difference, which is the apparatus to move the fuel assemblies, sure there's the fuel assembly support movement, are above the level of the coolant salt. Now this is actually hugely helpful because you are not having to do mechanical things inside the molten salt, which simplifies the engineering quite a lot and also means you can see what you're doing. In sodium reactors, these things are immersed meters below the surface of the sodium, and there is a reason for that which I will probably come back to later in the talk. Okay, so just going through the reactor step by step. We start with the fuel tube. The fuel tube is made of the same steels we make sodium fast reactor fuel assemblies from, probably HG9 in our case. It has a gas plenum to collect the fission gases and hold them up long enough for the particular xenon-137 to decay to cesium-137 so it doesn't escape the tube in that way. At the top of the tube there is a gas vent, which is a non-return valve, so that the excess gases can bubble into the coolant. Those fuel tubes are put together into a fuel assembly with a wrapper made again of the same materials used in sodium fast reactors. Those fuel assemblies are put together into the basic reactor module. This is a modular reactor, but not modular in the context of conventional small modular reactors. I'll come back to that. This is a factory-produced 150 megawatt electric module. It basically contains all of the engineering equipment for the reactor in the module. It contains heat exchangers, the pumps, the apparatus for moving the fuel assemblies themselves, and quite a few other things. All the instrumentation, contains the control blades, all of that in the assembly. That assembly sits in a tank along with other assemblies. In this case, this is our smallest version of the reactor. It has one full assembly in the middle and two half assemblies at the outside. Between the modules, rather not the assemblies, between the modules are control blades which are used only to shut the reactor down. They are not control mechanisms in the sense of adjusting reactivity. They're either in or they're out. If they're in, the reactor is shut down. If they're out, the reactor is live. Those modules allow this reactor to do something which I think very few other reactors can do, which is scale. So the previous slide showed one main and two half modules. That's the smaller size, which is practical. We can put up to 8 modules into a single reactor tank, shown on the upper right up here. And that will create a reactor up to 1 gigawatt in size. In principle, it could go higher, but that's probably somewhere around the optimum. This is quite a big deal economically. There is a problem with what I would call conventional small modular reactors. That's reactors where if you want a decent sized power station, you need to put half a dozen reactors onto the same site. You gain the advantage of modular factory construction with such reactors, but you lose the economy of scale. And economies of scale are very real. With the design of the Stable Salt Reactor, we achieve the benefits of the modular factory construction. So we build basically the entire nuclear engineering part of the reactor in the factory, but we maintain the economy of scale of having a single reactor, single control room, single fuel managing system, and therefore keep the economies of scale. Economically, that's actually quite important. Okay, just to give you a quick overview of the whole nuclear island, you have here the reactor tank. I'm not sure whether you can see my mouse on the screen. I hope you can. You can see the reactor tank here in the center in the dark grey. That's what the modules fit into. That has a containment dome above it, which is filled with argon gas, has an airlock for accessing it. Everything else here is fairly obvious, apart possibly from the emergency heat removal system shown here, which I'll talk a little bit about later, which allows the decay heat from this reactor to be passed directly to the atmosphere without needing any water supplies or pumps or indeed active intervention at all. All of the concrete structures on this slide are 1 meter thick, so that gives you a good size context, and size will become important, as I will show later. Okay, I have a best part of an hour talk on the design of this, which I don't have time to give here. So I'm just going to go very quickly through some of the key design decisions and why we made these. There's a lot more information on this available on our website for those interested. So the first decision was actually making a fast reactor rather than a thermal spectrum reactor. The reason to do that is that xenon in molten salt reactors is actually a real problem. Xenon and the xenon pit effect is very well known in nuclear and very well understood, rather the hard way, sadly. In molten salts, the xenon is going to bubble out, but you have to worry about how quickly it will bubble out, what the residual concentration will be, what are the kinetics of the xenon removal, how is the xenon going to move around with the salt. All of these things are actually safety critical understandings, and frankly, nobody does understand them properly yet. The molten salt reactor experiment, which was operating back in the 60s, actually suffered unexplained power transients of about 20%, which were ascribed to problems with the xenon effect, but never actually properly described. That has to be done. Okay, second, the chloride fuel. We use a chloride fuel rather than a fluoride fuel. Most of our competitors use fluoride because using chloride allows us to use standard steels, standard neutron tolerant steels like HT9. It allows that because we can stabilize chloride fuel with zirconium metal. You cannot stabilize fluoride fuel in that way. So this allows us to use existing, well understood materials. The coolant, zirconium fluoride based coolant, there are other options. We like the zirconium fluoride for two reasons. One is that it has a lower valence salt, zirconium difluoride, which gives the system a very strong and stable reducing potential, which again allows the use of standard steels rather than special high nickel alloys. The second thing is that zirconium, as it comes out of the ground, is always contaminated with hafnium, which might seem like a problem. But actually, by having the natural level of hafnium in our zirconium fluoride coolant, it converts the coolant into a really very effective neutron screen. So it protects the tank, the heat exchangers, from the neutron flux from the core without having to worry about any expensive and potentially replaceable screening. Tubes. We vented the tubes. This eliminates the pressure stress which would otherwise build up in the tubes. So tubes in sodium fast reactors are sealed and the gases build up to high pressures, which ultimately controls the limit or limits the amount of burnup you can achieve. We can vent tubes because the reducing state of the salt we have in there, in particular the zirconium stabilization, essentially eliminates the dangerous radioisotopes from the vented gas. There is detail about that on our website. On-power refueling. On-power refueling sounds like a great idea. It keeps your reactor operating all the time. That's not why we did it. By doing on-power refueling, you eliminate the hazard which happens when you're freshly fueled a reactor. You have far more fissile material in it than you need to achieve criticality. So you have a large amount of excess reactivity. Excess reactivity is a hazard, quite a serious one in fact. By having on-power refueling, you eliminate that hazard. The tank is air-cooled. This eliminates the need for water pumps and reservoirs. This is not unique to Moltex. Most of the smaller advanced reactors in the world are using passive air cooling. It's just a better idea. Underpinning all those design decisions is our safety philosophy, to eliminate rather than control hazards. I mentioned the two big ones early on in the talk: eliminating highly radioactive elements from the vapor source term, and eliminating the high pressures associated with both fuel and coolant. But it goes on. By using chemistry to eliminate the thermodynamic drivers of corrosion, we eliminate the problem of corrosion. We will have to monitor corrosion, obviously, but it'll be confirming it's not there. We are not managing corrosion. We're not replacing things because they corroded. We're not making sure that things haven't corroded too far before we replace them. We've eliminated the problem. Chemical reactivity within the nuclear island. We have no two chemicals within the nuclear island which will react violently with each other. That may seem really obvious, but putting zirconium and water together is a hazard. Putting sodium to water together is an almost insane hazard. We've avoided those. I mentioned excess reactivity and the advantage of continuous refueling. That removes what I call control rod hazard. Control rods are wonderful things, but we have blown up a number of nuclear reactors by misuse of control rods. If you have a system that requires control rods, you have a really very serious hazard. We've eliminated it. And emergency heat removal, removing the need for active intervention there is, again, obvious and done by many people. Okay, I've really skipped over the design. There isn't time to go into a lot of detail. If you're interested, there is a document in the Learn More section of our website which will give you a lot more detail of that. Okay, I want to quickly talk about the fuel that we use. It is a plutonium-based fuel. We're using plutonium and higher oxides as our fissile material. There's a key difference from MOX fuel here, which is actually very important. To make MOX fuel, you need very high purity plutonium. That's because you have to make a uranium oxide, plutonium oxide pellet with extremely precisely defined physical properties. We're making a molten salt. That means that our plutonium can actually be contaminated with more than its own mass of uranium left over from the reprocessing and lanthanides. And lanthanides are very important because they are the hardest thing to separate from plutonium. So we are able to use very low purity. What does that mean? It means it's much, much easier to reprocess spent oxide fuel into our fuel than it is into MOX fuel, which is just as well because nobody's ever really made MOX an economically viable option, as you'll mostly know. I won't go through this in detail. Again, there isn't time. It's a very simple three-step process. First is decladding, in our case, CANDU fuel bundles, because we are developing this technology in Canada, using chlorine gas, which produces zirconium tetrachloride as a waste product, except it's not a waste product, it's a useful output. That can be readily converted to zirconium tetrafluoride, which of course is our coolant salt. So it's not a waste, it's a useful output. The declad pellets go into an electroreducer. There's plenty in literature about this, I don't need to talk in detail, which reduces the oxide to a molten uranium iron alloy, melts at about 725 degrees centigrade. That has a waste product, which is the electrolyte from the electroreducer. And that electrolyte concentrates the major heat-producing fission products into about 1/100th of its original volume, which makes it a useful end-prop output, in fact, because that allows you to produce radioisotope-generated heat batteries, which in some parts of the world have a very real market. Finally, the uranium alloy is passed into a molten salt, molten metal contact system, which single contact between the salt input and the alloy extracts 98% of both plutonium and americium from the alloy into the salt. We actually do a two-stage contact, so we get 99.99% transfer, very efficient, leaving a uranium alloy behind, which is actually only intermediate level waste. Its radioactivity is almost entirely due to the depleted uranium in it. And that is the process producing our fuel. It's very simple, very cheap, and actually, and really very importantly, profitable. The net effect is to turn what for most nuclear reactors is a positive fuel cost, typically around £5 per megawatt hour, into a negative fuel cost. We actually make money by making our fuel. But we haven't taken advantage of that particular fact in our levelized cost of electricity calculations. We don't need to, we're already highly profitable. Okay, third technology underpinning Moltex, we call it GridReserve. Grid scale energy storage is a bit of a holy grail on nuclear power grids at the moment. They're needed. They're needed for renewables because renewables tend to produce power when you don't actually need it. But it's expensive. This is an advantage of the fact that the stable salt reactor has a high output temperature. If you're a PWR with an output temperature of about 300 degrees, you really can't practically store that energy. At 600 degrees, which is our output temperature, it becomes possible to store that energy in a thermal store. This is not new technology. It's used in the concentrated solar power industry. Its cost is about 1/3 of the cheapest battery storage technology currently envisioned, much cheaper than what's currently on the market. It's a very simple system. You simply take the output heat from the reactor, store it in molten salts. It's actually a nitrate salt in big storage vessels, and then use it when you want the electricity. So very, very simple concept. What I've shown here on this slide is what our preferred deployment model for the Stable Salt Reactor. This has the reactor itself, a 1 gigawatt electric power output. That is coupled to a primary heat store, which is where it puts the heat initially goes. That is a nuclear safety functioning part of the system. So when the reactor is shut down, that primary heat store is also used to manage the decay heat over the first several hours when it's being produced at a high level, and therefore it is a nuclear safety critical component. However, the salt is then transferred from that to the secondary heat store, which is much, much bigger, and from the heat store is used to go to steam generators and turbines. Two things from this slide to take. The first is that that secondary heat store and the boilers and the turbines have no function in nuclear safety whatsoever. They actually function essentially in the same way that demand on the electricity grid operates for a conventional nuclear power station. As such, it can, depending on the country, be outside the nuclear site boundary, or in other countries where you don't license activities, outside the nuclear regulated activity region. That reduces a great deal of cost and uncertainty. The other thing it does is it allows you to link much bigger turbines to your reactor than you otherwise could. So this model, we have a 1 gigawatt reactor feeding 3 gigawatts of boilers and turbines. That means this operates as a 33% capacity peaking plant, which is actually about typical capacity factor for a combined cycle gas turbine. When you do that, the capital cost is around £600 per kilowatt electric, which is comparable to a combined cycle gas turbine system. And with that cost electricity of £41 per megawatt hour. And that's based on pessimistically assuming current fuel price, and our price fuel expected to be better than free, and current operating costs, which again would expect to be able to reduce. But we're being conservative. The economic consequences of that system are actually huge. This is UK data. This shows the average over a year of the premium paid for electricity by the grid over the course of your typical day. This is actually 2016 data averaged over the whole of that year. Early in the morning, during the dark hours of the night, electricity has low value. Its value is 25% below the average. Then you have a morning peak, and people turn their kettles on, get ready to go to work. You have an afternoon lull when people are at work. Then you have an evening peak when people come back home, turn their TVs and kettles on, and so on. So we would charge our grid reserve during the night, partially discharge it in the morning, charge it some more during the slack time of the day, discharge completely during the evening hours, and then charge up again. That price arbitrage, selling it when it's valuable, not when it's got low value, increases the revenue by over £10 per megawatt hour. In the UK, entry into the capacity market mechanism adds a further over £8 per megawatt hour to the revenue. And the increased cost of having the ability to do that is £7.68 per megawatt hour. So this is an enormously profitable addition to the reactor. Okay, I want to go finally back to capital cost, because as I said at the beginning, this is where it actually really counts. This is the graph I put up. Most people look at that and say, that's ridiculous, you people don't know what you're talking about. So allow me to try to convince you. First, there are technical reasons why this reactor will be considerably cheaper. Eliminating instead of controlling hazards really is much cheaper. Not having high pressure systems in the nuclear island. High pressure systems are expensive. Very, very thick walled, very, very high integrity. They're expensive to make. We don't have any. The second surprisingly important aspect is the effect of high temperature. I mentioned that high temperature allows you to use grid reserve. It also allows you to use standard steam turbines of the type that are produced in their dozens or hundreds around the world for combined cycle gas turbine systems. Those turbines cost about 1/6 of the cost of corresponding power pressurized water reactor turbines. That's for two reasons. A PWR turbine operates on very poor quality steam, low temperature, low pressure, and is therefore considerably bigger. The second is there's no demand for them. Each one is bespoke and therefore you lack the economies of production in scale. And then there are other factors like we don't need cooling ponds for our spent fuel, we don't need a fuel store because it continues to refuel. All of these save money. I have to say I haven't convinced anybody with those arguments of our cost being low. This is slightly more credible. So we had our nuclear cost estimate done independently of ourselves by Atkins, according to their standards. We didn't tell them how to do it. They told us how they would do it. This cost estimate made no allowance for benefit from modular build. It was based entirely on the assumption of building it on site in the UK, which is the most expensive place in the world to build a nuclear reactor. Even that doesn't convince many people. I find that the side that actually does convince most people is this one. Size really does matter. This is, to scale, a comparison of an AP1000, which in my personal view is the best and probably the smallest of all the PWRs, with a stable salt reactor of the same power. Both of these are 1,000 megawatt size. That's an absolutely enormous difference, and you can see why it would lead to a huge difference in cost. How is that even possible? How is that even possible? Well, the key comes to understanding why the pressurized water reactor is so big. This is a cut through of, this is the AP1000. Down there in the middle is the nuclear reactor core. It's really quite tiny. In the containment vessel has to be big for a number of reasons. First of all, it actually needs a lot of empty space to dissipate the steam explosion that it might have to survive. So you have a meter thick concrete wall, but if you don't have space for the steam explosion to dissipate before the shockwave hits that wall, it will breach it. Secondly, inside the dome you have some very, very big components. You have pressurizers, you've got very large high pressure pumps, but the biggest of all is you have your steam generators, which are huge, occupy a very large fraction of the volume inside there. The SSR doesn't need the empty space to split the steam explosion. There is no steam in there. There's no pressure. It doesn't have pressurization, and the pumps are actually in the tens of kilowatt range. And most important, the steam generators are not in the reactor. They're not even on the nuclear site. They are outside the nuclear licensed area, off with the grid reserve. That's the technical driver for why the size is so small. Both of those, the AP1000 and SSR, they both have 1 meter thick containment walls. We are not skimping on containment. We may not need to contain the explosion. We do need to keep out low-flying aircraft, so we have to survive the same stresses. But we do it on a much smaller scale. So, skip over this one because I've actually talked through this one already. The key reason why we can argue for the entire secondary heat store boiler system turbines being outside the nuclear regulated area is because in the safety case, which is now well advanced for the SSR, we make absolutely no claim on function of that material outside the site boundary, none. It has no role in any safety function at all. And that, of course, is the definition of when it should be nuclear regulated. Okay, what does the impact of this on cost? Well, the overnight capital cost for the reactor is low, but it also, of course, has a lot of uncertainty. Nobody's built one yet, and nuclear has something of a reputation for overrunning cost estimates, to put it mildly. Because of this separation of the boiler turbine heat source system from the nuclear site, we can actually break these capital costs down. All of this material outside the nuclear site is absolutely industry standard material. It's like a combined cycle gas turbine without the gas turbine. As a result, the cost estimates for that are very high confidence. It's all material which is already built at scale multiple times in the world. And the pie chart there shows the breakdown between the cost of the rest of the plant, the non-nuclear regulated part, and the nuclear site. This is the nuclear site, not just the reactor, I should emphasize. And roughly 2/3 of the cost is the rest of plant. That means if you apply all the pessimistic assumptions, optimism, bias, and so on, to the cost estimate for the nuclear site, even if we have a 100% cost overrun on the nuclear site, we still end up with a capex of £950 per kilowatt, which on this graph is that extra bit of bright red on top of our cost. In other words, if we double or even triple our nuclear costs, we are still comfortably within that green zone where nuclear has the potential to become the dominant energy source. That is absolutely what we are setting up to do. We see a world where the world has two major sources of energy: renewables, which operate at zero marginal cost, with stable salt reactors providing the dispatchable energy needed to complement the renewables. That is the vision of our company. So at that point, having run over slightly my time, I apologize for that. Now, thank you all, and I'm quite happy to answer any questions if I can work out how to make this technology on the right side of my screen work to my benefit. Thanks very much, everybody.
Thanks, Ian. The questions can be typed into the questions panel, and I can help read those out if you're having trouble seeing those, Ian. I think there's been one that's come in throughout the presentation from Angus Cook, who's asked, why are the MS...
Why are the modules grouped with half module caps at the end?
Mm-hmm.
Good question. And in an earlier version of this presentation, we actually had our smallest module being two full-size modules. The reason is simple, is that we need, in order to be able to confidently shut down the reactor with control blades positioned between the modules, we actually need two slots within the core to do that. With two full-size modules, there's only one slot within the core, and the combination of blades, shutdown blades there and at the ends isn't enough. So we move to the one full and two half modules. The larger ones still have the two half modules at the end, but they have large numbers of full modules in the middle. So it's all about reactivity control. I've got another one here. What is the status of licensing at the moment for the SSR? So we have commenced the Canadian Nuclear Safety Commission vendor design review. We are moving ahead in Canada much faster than in the UK, although we have hopes for the UK once the government gets its advanced modular reactor program and competition back on track. But we've commenced the Canadian vendor design review, and our expectation is that we will move from that into a site licensing again in Canada, with the intention of having the reactor on the grid by 2027, which we believe is achievable in Canada. Although sadly the analysis that concluded, which was done for us by Amick Foster Wheeler, that concluded 2027 was possible in Canada, concluded that it would need another year or two in the UK because things are a little slower here. But nonetheless, that actually works quite well for us. You're welcome, Andy.
Okay.
I wish I could pop these out. I'm trying to look at them in a very, very small
So if you've got if you
screen.
click the little arrow, they should pop out. We've got question from Niels Kenwood. Are there any
Oh, yeah.
pilot?
Sorry, you have to read them out for me.
Yep.
Yep. Go ahead.
Yep. So it's, are there any pilot plant plans ahead of full deployment?
Very good question. No. And in that, we actually have that in common with all the other serious vendors of advanced reactors who are moving to a model where the first reactor built will be a commercial unit, which I think is right. I think that back in the 70s there was a good argument for doing a quick and dirty small reactor, seeing how it worked, get data and then do the bigger ones. In the modern world, where the regulatory system really requires you to go through all the hoops for a small prototype as you would for a full-size one, it doesn't make sense not to go straight to a commercial scale reactor. So our first reactor will be 300 megawatts. We will scale up after that up to 1,000 megawatts is our intention, but the 300 megawatt is commercially highly viable.
Yeah, I think. Oh, okay. We've got one more come through. This, I think we should make this the last question, just so we can stay within the hour. So it's from Alexander Terrell. It is, how confident are you that the regulators will not insist on a full probabilistic evaluation of the rest of the plant on the grounds that an event here might trigger an event in the nuclear island?
Okay, this is something which we have discussed extensively, and the concept has been has not led to any strong negative response. The last part of that question is actually quite important. Any activity within within a boundary around a nuclear reactor which could impact on the reactor must be regarded as a potential external hazard. And so there are two reasons why you would worry about something outside. The first is if what's outside is actually important to the safe functioning of the reactor, and that's what we avoid. The second is, can an accident outside impact on the safe function of the reactor? So the classic thing, of course, is turbines disintegrating and turbine blades flying out. And so the external heat store and boilers and turbines would be regarded in just the same way as any other potential external hazard to the nuclear site. You would take it into account, but you take it into account as an external hazard, not as something important to safety. It's a really very important difference there. So, for example, if you were putting a nuclear reactor in the middle of a chemical plant, as an industrial unit, then you would absolutely worry about what happens if that chemical plant blows up on the performance of the nuclear reactor, even though the chemical plant's got nothing to do with it. It's just like an external hazard. If you have a hydroelectric dam upstream from your nuclear reactor, you'd worry about the hydroelectric dam breaking and flooding the reactor. It's an external hazard, and so the grid reserve and the boilers turbines would be an external hazard in just the same way. That's very different in regulatory terms to it having a role in the safety case. So if I'm seeing there's actually other questions on the board which I can't actually
I think
read, but if we haven't run out of time, I guess you should probably draw this to a close, Andrea.
Yeah, I think is it all right if there are any further questions that people contact you by email? Is that all right?
Yeah, that'll be fine. I think
Okay.
I'll with that.
Okay, great. All right. Well, thank you everyone for logging in today, and thank you very much, Ian, for hosting the webinar. And we'll draw this to a close now.
Very good. Thank you very much, everybody.
Okay. Bye.